Dear students and my dear friends, today in this session of production and industrial engineering, we are going to discuss some topic from the subject of industrial metrology and statistical quality control, which is one of the important subject for production and industrial engineering students. The topic we are going to discuss today are inspection, standards of measurement, interchangeability, accuracy and precision, international, national, line and wavelength standards. So let us start with today's first topic. So if we discuss about the rationale of this subject, that is why this subject is important for the students of production and industrial engineering, then the diploma holders studying this course are responsible for measure and inspection for ensuring quality of the product on the shop floor. So for this purpose, knowledge and skill about standards of measurement, limits, fits and tolerances, types of inspection and various measuring instruments and SQC means statistical quality control is necessary. He or she must be aware of quality system, hence this subject. So first topic is inspection. So what is inspection? An inspection is most generally an organized examination or formal evaluation exercise. So in this engineering activities, inspection involves the measurements, test and gauges applied to the certain characteristics in regards to an object or activity. The results are usually compared to specified requirements and standards for the determining whether the item or activity in line with these targets. So inspections are usually non-destructive. A surprise inspection tends to have different results than an announced inspection. So leaders wanting to know how others in their organization perform can drop in without warning to see directly what happens. So if an inspection is made known in advance, it can give people a chance to cover up or to fix their mistakes. So this could lead to distorted and inaccurate findings. A surprise inspection therefore gives inspectors a better picture of the typical state of the inspected object or process than an announced inspection. So it also enhanced external confidence in the inspection process. Need of inspection, that is why inspection is needed in the industry. First is to ensure that the part, material or a component conform to the established standards. Second is to meet the interchangeability of manufacturer. Third is to maintain customers' relation by ensuring that no faulty product reaches the customers. Fourth point is provide the means of finding out shortcomings in manufacture. The results of inspection are not only recorded but forwarded to the manufacturing department for taking necessary steps so as to produce acceptable parts and reduce the scrap. Fifth point is it also helps to purchase good quality of raw materials, tools, equipments which governs the quality of the finished products. Sixth point is it also helps to coordinate the function of the quality control, production, purchasing and other departments of the organization. Seventh point is to take decisions on the defective parts, that is to judge the possibility of making some of these parts acceptable after minor repairs. The various units of measurement. A units of measurement is a definite magnitude of a physical quantity defined and adopted by convention and or by law. So that is used as a standards for measurement of the same physical quantity. Any other value of the physical quantity can be expressed as a simple multiple of the units of measurement. For example, length is a physical quantity and the meter is a unit of length that represents a definite predetermined length. So when we say 10 meters or 10 m, we actually means 10 times the definite predetermined length called the meter. So the definition, agreement and practical use of units of measurement have played a critical role in human endeavor for early ages up to this day. So the different systems of unit used to be very common. Now there is a global standards, the International System of Units, shortly named as SI units, the modern form of the metric system which we are generally using in the industry. So in physical and metrological units are standards for measurements of physical quantities that need clear definitions to be useful. So reproducibility of experimental results is central to the scientific methods. A standard system of unit facilitate this scientific system of units are a refinement of the concept of weights and measures developed long ago for commercial purposes. So science, medicine and engineering often use large and smaller units of measurement than those used in everyday life and to indicate them more precisely. The judicious selection of the units of measurement can aid researches in the problem solving process. So international system of units. So if we define this international of system units, the definition is a quantity in the general sense is a property ascribed to phenomena, bodies or substances that can be quantified for or assigned to a particular phenomena, body or substance. So examples are mass and electric charges. A quantity in the particular sense is a quantifiable or assignable property ascribed to a particular phenomena, body or substance. Examples are the mass of moon and the electric charge of the proton. So a physical quantity is a quantity that can be used in the mathematical equations of science and technology. So a unit of particular physical quantity defined and adopted by convention with which often particular quantities of the same kind and compared to the express their values. All physical quantities can be expressed in terms of several basic units as in the industrial field. So base quantity, name and then the symbol. So if base quantity is length, its name is determined as meter and symbol is small m. Similarly, base quantity is mass, name is kilogram, and symbol is kg in small. And base quantity time, name is second, and symbol is small s. Similarly, base quantity electric current, name is ampere, symbol is capital A. Base quantity temperature, name is Kelvin, and symbol used is capital K. Base quantity amount of substance, name is mole, and the symbol used is MOL. Similarly, base quantity luminous intensity, name is candela, and the symbol used for candela is small cd. Derived units. So, other quantities called derived quantities are defined in terms of 7 base quantities via a system of quantity equations. The SI means derived units of these derived quantities are obtained from these equations, and the 7 SI base units. Examples of such SI derived units are given, where it should be noted that the symbol 1 for quantities of dimensions 1, such as mass fraction, is generally omitted. Derived quantity is area, name specified is square meters. Expressions in terms of SI units is small m square. Similarly, derived quantity is volume, name prescribed as cubic meter. Expressions in term of SI units is m small m cube. Derived quantity speed, velocity, name prescribed as meter per second. Expression in terms of SI units are small m oblique small s. Similarly, derived quantities acceleration, name prescribed as meter per squared. Expressions in term of SI units small m oblique small s square. Similarly, derived quantity is mass density, name prescribed is kilogram per cubic meter, and expression in terms of SI units are kg per m cube. Similarly, derived quantity is force, name specified is newtons or capital N, and expression in terms of SI units is m ks s raised to power minus 2. Similarly, pressure is name specified in Pascal, and symbol is small m minus 1 kg s square minus 2. Energy work name specified joules or J Newton meter, and symbol specified as m square kg s raised to power minus 2. Similarly, electric potential name specified as volt capital V, so symbols as m square kg s raised to power minus 3 capital A raised to power minus 1. Standards of measurements. The law of physical and expressed as mathematical relationship among physical quantities. Most of these quantities are derived quantities, or they can be expressed as combination of some basic quantities. There are mainly 3 quantities in physical or mechanics. These are length, mass, and time. So, interchangeability. What is interchangeability? An interchangeable parts is one which can be substituted for similar part manufactured to the same drawing in either times production used to be confined to small number of units, and the same operator could adjust the mating components to obtain desired fit. With time, the concept of manufacturing techniques kept on changing, and today the same operator is no more responsible for manufacture and assembly too. With economic oriented approach, mass production techniques were inevitable that lead to breaking up of a complete process into several smaller activities, and this lead to the specialization. As a result, various mating components will come from several shops. Even a small component would undergo production on several mechanics. Under such conditions, it becomes absolutely essential to have strict control over the dimensions of portions which have to match with other parts. So, any one component selected at random should assemble correctly with any other mating component in the production line, that too selected at random. So, when a system of this kind is ensured, it is known as interchangeable system. So, interchangeability ensures increased output with reduced production cost. So, accuracy and precision. So, what is accuracy and what is precision, and what is the difference between the two? So, if we define accuracy is how close a measured value is to the actual or true value. So, precision is how close the measured value are to the each other. So, in the fields of science, engineering, industry and statistics, the accuracy of a measurement system is the degree of closeness of measurement of a quantity to that quantity's actual or can say true value. The precision of a measurement system, also called reproducibility or repeatability, is the degree to which repeated measurements under unchanged conditions show the same results. Although the two words reproducibility and repeatability can be synonymous in colloquial use, so they are deliberately constructed in the context of the scientific methods. So, here if we look at this graph, in the horizontal axis, see on x axis we show the precision line. This is the precision value and this is the probability density. This shows the accuracy in this system. This is the reference value and this area shows the precision of this value. So, accuracy indicates proximity of measurement results to the true value, precision to the repeatability or reproducibility of the measurements. A measurement system can be accurate but not precise. So, precise but not accurate, neither or both. So, for example, if an experiment contains a systematic error, then increasing the sample size generally increases precision but does not improve accuracy. So, the end result would be a consistent yet inaccurate string of results from the flawed experiments. So, eliminating the systematic error improves accuracy but does not change precision. A measurement system is designed or designated valid if it is both accurate and precise. So here in this diagram we can compare accuracy with precision. So in the first diagram, if we see, this is of good accuracy but poor precision. Here round this shows a hit dot board, and these are the arrows which hit this dot board. This hitting is, can say, good accuracy but poor precision, because these all arrows are far away from each other. Similarly, in this case, we can say this is of poor accuracy but good precision, because all these arrows hit a side of this dot ball. Similarly, in third case, this is of good accuracy and good precision, because all these arrows hit this dot ball in the center point. So this is the basically difference between the accuracy and precision. Comparison chart between accuracy and precision. So about accuracy, a term used in measuring something. Similarly, in precision, a term used in measuring something. So if we define accuracy, the accuracy of an experiment object value is a measure of how closely the experimental results agree with a true or acceptable value. So similarly, if we define precision, precision of an experiment object value is a measure of the reliability of the experiment or how reproducible the experiment is. Similarly, if we see the measurement, in case of accuracy is single, in case of precision is number of measurements are needed. Similarly, if we talk about the quality, in the first case it does not speak of the quality, second case it speaks of the quality of the product. So if we see the uses, the physical and engineering statistics, etc., in the second case also the physical engineering and statistics, etc. So next is international standards. International standards are standards developed by international standards organizations. International standards and available for consideration and use worldwide. The most prominent organization is the International Organization for Standardization. So international standards may be used either by direct application or by a process of modifying an international standards to suit local conditions. The adoption of international standards result in the certain of equivalent to national standards that are substantially the same as international standards in technical contents, but may have one editorial differences as to appreciations, use of symbols and measurement units, substitute of a point for a common as a decimal marker, and second is differences resulting from conflicts in governmental regulations or industry specific requirements caused. So by fundamental climatic, geographical, technological or infrastructural factors, or the stringly of safety requirements that a given standard authority consider appropriate. So international standards are one way of overcoming technical barriers in international commerce caused by different among technical regulations and standards developed independently and separately by each nation. So, national standard organization or company standards, technical barriers arises when different group come together, each with a large user base doing some well established things that between them is mutual incompatible. Establishing international standards in one way of preventing or overcoming this problem. So, definition of International Organization for Standardization, or in short we can say ISO, the world's largest developer and publishers of international standards. The ISO is a network of the national standard institutes of 163 countries, coordinating by the Central Secretariat in Geneva. For example, in a currency contest, ISO 4217 is the international standard established by the ISO that specifies the structure for the three-letter codes used to describe the many currencies used around the world. Standard organizations. So, there are many standard organizations that establish and implemented standards. Some of the most prominent are American Petroleum Institute, shortly named as API, American Society for Testing and Materials, shortly named as ASTM, British Standard Institution, shortly named as BSI, European Computer Manufacturer Association, shortly named as ECMA. Similarly, Institute of Electrical and Electronics Engineering, shortly named as IEEE. International Electrotechnical Commission, shortly named as IEC, International Organization for Standardization, shortly named as ISO, Telecommunication Industry Association, shortly named as TIA, International System of Units, shortly named as SI units, International Telecommunication Union, shortly named as ITU, Organization for the Advancement of Structured Information Standards, shortly named as OASIS, Universal Postal Union, shortly named as UPU, Social of Motion Pictures and Television Engineering, shortly named as SMPTE. International System of Units. The International Systems of Units, abbreviated as SI from the French language, so is the modern revolution of the metric system. It is the world's most widely used system for measuring units, so both in everyday commerce and in science. The SI was developed in 1960 from the meter kilogram second system, shortly named as MKS system. So, rather than the centimeter gram second system, shortly named as CGS system, so which in terms had many variants. During its development, the SI also introduced several newly named units that were previously not a part of the metric system. The original SI units for the 6 basic physical quantities were meter M, which is SI units for length, second S, which is SI units for time, kilogram, kg, which is SI units for mass, ampere capital A, which is SI units for electric current, degree Kelvin capital K, which is SI units for thermodynamic temperature, candela CD, which is SI units of luminous intensity. The mole was subsequently added to this list and the degree Kelvin renamed as Kelvin. So, there are two types of SI units: base units and derived units. So, base units are the simple